the thing at the very top.
Yes, so this.
Don't worry about that. We can't see that. As long as it's not blocking
Okay.
for you, don't worry about it. Yeah.
So I will just try to move it so it's to the top. Then is that it covers part of the slide, so I can see.
Yeah, and we can't see that, so you're all good.
Okay, I'm going to go ahead and start the recording.
Okay.
All right, whenever you are all ready.
Okay, I'll go ahead and introduce. Good morning, everybody. Good afternoon to our speaker. Good morning to the rest of you. Thanks so much for joining today. I'm very excited to introduce Dr. Irina Gorodetskaya. She's a researcher in the area of Earth and environmental sciences with an emphasis on atmospheric sciences. And the focus of her work is on polar meteorology and climate, particularly the hydrological cycle processes, combining observations and regional climate modeling. Some background, she received her diploma from St. Petersburg State University in Russia from the Department of Geography and Geoecology in 2000. She then went on to do her master's and PhD studies, both at Columbia University in New York in the Department of Earth and Environmental Sciences at the Lamont Doherty Earth Observatory. She went on as a postdoctoral researcher at a couple different places in Europe at the Laboratory of Glaciology and Geophysics of the Environment in France, and also at the University of Leuven in Belgium. Since 2016, she's been a researcher in the Center for Environmental and Marine Studies in the Department of Physics at the University of Aveiro in Portugal. She's especially keen on gaining new knowledge about polar regions via observations, and has participated in expeditions in the Arctic, in the Antarctic, and in the Southern Ocean. She's currently preparing with a group of international colleagues, working with the Year of Polar Prediction Winter Special Observing Period in Antarctica. She's a member of the steering committee of the 8-year SCAR Scientific Research Program on near-term variability and the prediction of the Antarctic climate system, and is one of the lead authors on the IPCC 6 assessment report. So her particular interest is Antarctic precipitation and atmospheric rivers, which is the focus of her talk today. She also wants to share both the importance and the amazing beauty of Antarctica and has been engaged in many outreach activities. So the title of her talk today is Precipitation in Antarctica and the Role of Extremes. And with that, I will turn it over to Dr. Gorodetskaya.
Thank you very much, Claire, and everybody for inviting me for this opportunity to talk for you all about Antarctic precipitation. And I wish I could meet you all in person, but it's also great that I can give this talk remotely, and I will try to do my best to convince you about the importance and the beauty of Antarctica. And please interrupt me, ask me questions during the talk. I will really appreciate like more active discussion. And I will actually do a journey in about precipitation and atmospheric rivers. So there will be a lot of material. Hopefully I didn't, won't go too much over time. I'll just put the time in. And yeah, so let's start. So I will talk today about precipitation in Antarctica and the role of extremes. So I'm working currently in Portugal, which is not really a polar country, I know, but it's we actually have a really active community, so which is part of the Portuguese Polar Program. And here it's actually on the first slide right away. I would like to show you the contrast in Antarctica between the nice weather. So the first picture I took so during the summer night at the Princess Elizabeth Station. So with the nice weather, and we see this when we were still living in the camps before the station was finished. So it was actually a really nice experience. And the same camp, I think it was really taken from the same point during the whiteout, during the precipitation and the blowing snow event. And you can see the striking, the difference in the two images. So today I will especially talk about the role of observations and the difficulty also of observations, but I will more touch about the processes. So I will be using observations to discuss the important processes that are responsible for precipitation in Antarctica. Okay, how do I move to the next slide? So the motivation also to understand Antarctica, as it makes a part of the global climate system. And as we know from the previous IPCC special report in 2019 that summarized the most recent literature, that we have a global warming that is occurring in the last 50, 70 years. So this is, we know from observations that the global temperature is increasing, and the projections using the different scenarios. So here we have the pessimistic scenario, the called RCP 8.5, and the more optimistic and the more effort-based scenario, RCP 2.6. We see that the global warming is projected to continue. And it depends also on us, like what is the rate of this future global warming. So cryosphere plays really a huge role in the changes in the Earth system. And here again, so from SROC report in 2019, so this is the cryosphere and ocean special report, we can see the changes that have been occurring in the cryosphere, as well as their interaction with the Earth system. So the changes include the significant decrease in the snow cover, decrease in the glacier mass, and increase in the temperature of the permafrost, and decrease in the sea ice in the Arctic. And in the Antarctic, we have decrease in Antarctic ice sheet and also Greenland ice sheet mass loss in the Arctic. And sea ice is more uncertain changes in the Antarctica, and we have the contribution of Greenland and Antarctica to the sea level rise. And changes in the cryosphere are related to the rest of the Earth via water, heat, and carbon dioxide and other fluxes. So it's really important to understand, to study and measure and understand the processes that are responsible for these changes in the both Arctic and Antarctic. So in particular, it has been shown recently that it's not the thermal expansion, but it's actually the contribution from the glaciers and the two ice sheets that are now the primary drivers of the already occurring sea level rise. And we have, so the projections for the end of the 21st century, so the sea level rise range from about 0.5 meter to almost 1 meter, depending again on the scenario that we would be using in projections. And we see again that it's rising, the sea level rise is projected to continue and to have a really huge range also by 2300. And again, so the two things to notice, so this is the global sea level rise here, and this is, the contribution of Greenland, Antarctic ice sheet, and glacier mass loss. And an important picture here is also, it's not only the increase and that we have an increase in sea level rise, the contribution from the ice sheets and from the glacier, but also the huge uncertainty, so which we still have to resolve because it depends on how the models are representing a lot of processes. And this is what we can do also with observations, to continue observing and to use them for model evaluation and improvement. So if you focus particularly on Antarctica, and this is a huge international effort from the so-called IMBY team. So that was a paper out in 2018, showing the mass loss from Antarctica. So we have so in total, Antarctica is losing mass, and actually the major contribution to this mass loss comes from the West Antarctic ice sheet. Also, we have significant contribution from the peninsula, and East Antarctica is less certain. And actually there are new studies since then which show actually that East Antarctica is most probably losing mass, even though, so this compilation of various observational and modeling techniques show that the uncertainty is huge. So this is what we also would like to resolve, like what are the contributing factors to this mass loss from different parts of Antarctica. And if you look at the high resolution spatial images of the changes that have been measured over both Greenland and Antarctic ice sheets, so this is from, again, recent publication using the ICESat and ICESat-2 satellite measurements. So we see that Greenland is losing a lot of mass along the periphery, but it's gaining mass over the central ice sheet. But overall, so here these are at the boundaries of various drainage basins. So we see that Greenland is losing mass everywhere. So if you just consider it by the drainage basins. A different picture is found for Antarctica. So we see that, yes, overall, the West Antarctica is losing mass, and this is the huge contribution, well, the important contribution to the entire Antarctic mass loss. And we see the really large differences between the West Antarctica and East Antarctica. So in the West Antarctica, we have significant mass loss along the periphery, and this actually continues into the western part of the Antarctic Peninsula, and also the insignificant loss over the ice shelves. While in East Antarctica, we have, and here we see the basins, so the Bellingshausen Sea Basin and the Amundsen Sea Basin, so they're actually losing mass primarily. But if you look at the Queen Maud Land, for example, here in the East Antarctica, so the satellite observations have shown that it has gained mass during the recent years. So this is from 2003 to 2019. However, some areas have shown primarily loss of mass, but this is just parts of Antarctica. And actually, it's one of the major conclusions also of the current IPCC assessment report, that parts of Antarctica are definitely, parts of East Antarctica are definitely losing mass, like here the Wilkes Land, but there is huge interannual variability. And West Antarctica is definitely losing mass, and Antarctic Peninsula is part of the West Antarctica is losing mass. So what are the key components of the mass balance in Antarctica? So this is an image of the part of the ice shelf, and we can see that we have the major contribution to the mass balance. So this is the surface mass balance, which comes from precipitation, so the snow accumulation. And then Antarctica, so it's the ice sheet is losing mass by the glacier acceleration and then calving of the ice shelves and disintegration. And mostly, so the loss of the ice shelves and loss of the buttressing is causing the, again, acceleration of the glaciers. But there is this important, and the loss of the ice shelves is from the basal melt primarily. So I will not go in details about this. And today we'll talk only about the precipitation component, which is, so this is an important balance. So we have to understand what are the processes and the spatial distribution of precipitation and how it balances with the ice discharge. So if you look at the more complicated image, so here, this is the total, so the components of the mass balance. And here in crosses, I marked the processes that are not important in Antarctica, but all others are important. So we see it's a really complicated picture. So when we are talking about the total mass balance, so we have the precipitation as the key positive component of the surface mass balance. And at the same time, precipitation in Antarctica, so it's mostly occurs at the snowfall, but we have recently we have this accepted study, the first author, Etienne Mignon, where we showed that there is a significant rain actually also occurring on the coastal Antarctica and also in the Antarctic Peninsula. So the precipitation, so both snowfall and rainfall, actually, they are positive components of the surface mass balance, because when rain refreezes, so then it also adds mass to the ice sheet. So only when we have the loss of the rain runoff, so that's when the melt is actually going into the ocean, so then we have a negative contribution to the surface mass balance. So here it is shown in the blue, so the surface melt and surface meltwater runoff into the ocean, which can be also coming from the refrozen water if there are any processes within the glacier, so within the ice shelf. So another important negative component of the surface mass balance is sublimation. And there is a huge contribution, both positive and negative, of the windborne snow, so the drift itself. Also in the central Antarctica, we have important deposition of snow. So for example, like on the South Pole, like in the Dome Sea, so really in the interior of Antarctica. And today I will be focusing on this, so the solid precipitation part. So the processes behind the precipitation, mostly snowfall. Why do we see this huge differences in and huge uncertainties also in the present and also in the future mass balance of Antarctica? So this is the recent study by Irina et al., which showed the components of the mass balance by region. So here we see the West Antarctica, East Antarctica, Peninsula, and the total. And here what is important is, so in blue line, so this is showing the surface mass balance. So this is from RACMO model, and we have discharge at the different basin boundaries, and like violet, magenta. So this is the total mass loss. So overall, we see that there is a loss from all regions in Antarctica, and this is the new study that I mentioned that actually showed that East Antarctica overall is losing mass. And again, the uncertainty is huge. So this is one of the methodologies that actually doing these estimates, but this is also being put together now with new IMBY results. And an important component, so the focus of today's talk is the precipitation, so the surface mass balance. You can see that there is no significant trend actually that has been found during the instrumental period. So this is from 1979. So we know that since the beginning of the 20th century, we do have a positive trend that was measured in the ice cores in the West Antarctica and in Peninsula. But if you focus on the instrumental period, actually we see that the interannual variability in the surface mass balance is really large, and it's masking any possible trend that can be existent in precipitation. So what is standing behind this huge interannual variability of precipitation? So if we are, if we talk about the different components, if we just focus on one year of precipitation. So here, this is the measurements from the Princess Elizabeth Station in Dronning Maudland, which, as you remember from the previous slides, I showed that it is probably gaining some mass, but interannual variability is huge. So what do we know from observations in this particular region? And the observations I will be showing you, so this is the precipitation comes from the micro rain radar, and then we also were using the snow height measurements from the automatic weather station. So the changes during the year show that if we focus on the snowfall, so this is the red line, so we see that there is this stepwise increase. So this is a cumulative surface mass balance. So the red is the snowfall, this gray, so the black line and the gray background. So this is the measured snow height. Sorry, the red is the measured snowfall. And this is actually the first time when we had measurements or direct measurements of snowfall using the radar in Antarctica. So this is, it was the first study. So here I'm showing the 1 year of during 2012. And we see also the loss. So this is the contribution from the sublimation and from the snowdrift, which we calculated using different parameterizations. So the key message here is that we see the stepwise increase. So during this 2012 year, which was a normal year for Princess Elizabeth, for Dronning Maudland, which had overall about 110 millimeter water equivalent of precipitation, but only half of it was accumulated. So, and this accumulation, we see that it follows actually. So snow accumulation on the surface. So we have the peaks following the stepwise increase in the snowfall. So despite the removal, significant removal of precipitated snow by snowdrift and by sublimation. And again, this is the point measurements. So we see that the total yearly accumulation here, it happens in specific, the peak values, right? So we have just specific snowfall events, and we can count them. Like, so there are just several events during the year that are actually responsible for the overall snowfall and accumulation at this location. And what is important is the contribution of extreme precipitation events. So that was shown by the paper, by the study of Turner et al. In 2019. So they took the highest percentile, so it was the from 90th to 99th percentile of precipitation. And here in the map, so the color is actually shows, so the darker red shows the up to 75% of the annual precipitation contribution from the extreme precipitation events. So that means here in the coastal and also on the coastal areas and the ice shelves and escarpment areas all around Antarctica, and especially so here in the joining moundland, the peninsula region, and here in the Ross Sea, the larger Ross Sea region. So we see that the contribution of extreme precipitation events, extreme snowfall events, is really important. So it's basically we can have several events per year which determine the overall annual amount of precipitation and surface mass balance. And we know that the local sources of evaporation in Antarctica, they are close to zero. So all the precipitation that comes to Antarctica actually comes with the exotropical cyclone. So we have advection of moisture and clouds and precipitation formation, and also advection from lower latitudes. So here's just one figure that I would like to show. It's a summary. So just to bring your attention, the frequency. So this is in the contours show the highest frequency of occurrence of the exotropical cyclones, and the colors here show the where the moisture is actually coming from. So this is the evaporation region. So we can see that the exotropical cyclones, they're just circling around Antarctica. So we have this over the Southern Ocean. However, the important moisture contribution comes from lower latitudes. And what we have found during the recent years that, so if you look at specific exotropical cyclones, and not all cyclones have the same intensity, but some of them are associated with what we call atmospheric rivers. So these are the corridors of really anomalously high integrated water vapor amount and transport. So mostly poleward, but also we have some zonal atmospheric rivers as well. But here the contribution to Antarctica comes mostly from this meridionally oriented atmospheric rivers. As I'm showing here in the two examples, so one it's actually happened in 2009 and one in 2011. And both years they had anomalous snowfall and accumulation in joining moundland. And what we found is actually just several. So we counted like 4 events in 1 year and 5 events in another year, just several of these atmospheric river events that contributed to this anomalous surface mass balance in joining moundland. So this is I will now walk you through the structure of these events using the specific examples. So this is the spatial, the two-dimensional picture of these 2 events. So this is just showing the integrated water vapor in centimeters, and the arrows show the associated integrated moisture transport towards Antarctica, which is here. So I just isolated. So the arrows actually showing only the area within the atmospheric river contour that identified using a specifically developed algorithm for atmospheric rivers detection in Antarctica. So, and if you look at specifically at the this year, so in 2011, and the events which happened in February, which contributed a lot to the overall total yearly accumulation at this location. So we can see this, the measurements and the, so this is actually from from Erie interim, but and overlaying with the accumulation at Princess Elizabeth Station. So we see that we have several peaks of total precipitation, and this is the total cumulative that I showed earlier. And here for the entire year, we see that there was specific, so several events that contributed to the overall high accumulation during that year. And the event in February was really significant. So this event really brought more than 25% of the total annual accumulation at Princess Elizabeth Station in Dronning Maudland. So, and they, to give you a perspective of this event, so if you look at the different measurements, so we have the Grace anomaly showing the significant accumulation over this particular region in Dronning Maudland. We see we have the Erie interim integrated net precipitation, an increase, and the measured precipitation by cloud set. So all showing significant increase, and specifically, so this year's 2009. So you see this a really huge increase. Then 2010 was really dry. It's really anomalously low precipitation in Dronning Maudland, and then we have another peak in 2011. So what was actually happening in Dronning Maudland and why we have this anomalous snowfall events? So we looked in details in this event in February 2011 using ERA 5 reanalysis. So here we can see on the left the contribution of this event to precipitation from 14th February to 18th February. So we see that there were two peaks of precipitation and overall the significant accumulation, and we see also the large area affected during just one event. So here we have the accumulated precipitation over the whole duration from 14th February to 18th February. And the star shows the location of Princess Elizabeth Station. So we had actually measurements of snowfall. And it's actually, we also use these observations to evaluate the ERA 5 reanalysis, and it showed really good capacity, good to capture this anomalous precipitation, while it was underestimating the total amount of precipitation. So here in blue is the ERA 5, and in yellowish is the observed precipitation at Princess Elizabeth Station. So we see that the two peaks are captured really well by the ERA 5 reanalysis, and also so we have the peaks here, and then there's also continuation. So this the second major peak and the hiatus. So it's really well captured by ERA 5. So it was really impressive that this reanalysis has a lot of improvements over Antarctica specifically. And this I should mention that there is still a huge uncertainty in the derived amount, so the snowfall rate from the radar, because so this we are showing actually one of the ZS, where's my mouse? The ZS relationships, just to have a comparison with ERA 5. So I'm not showing the uncertainty here, but actually the ERA 5 is within the uncertainty of the various radar refractive reflectivity to snowfall rate conversion ratios, which depend on the snowfall microphysics. So we still, we have to reduce the uncertainty also in observations. So if we look at the event in particular, and we have a really strong evolution of the event. So here we see the evolution from the 15th of February, so A, B, C, D. So we have from the left to the right, and then you go down C, D, E, F. So these are the different stages, the evolution of this 2011 event. And we see what they are. We had a low pressure system, which was a large scale synoptic pressure system, which was already associated with a significant integrated water vapor transport, meridional transport towards Antarctica, and intensifying with time, with the mesoscale cyclone developing in the lee of the synoptic scale system and intensifying. And this second peak is actually associated with this mesoscale cyclone that was developing, bringing intensification in the second phase of precipitation. And here we see that the fully developed atmospheric river And it was found in between, so just in the pre-cold frontal sector, so really narrow and strong flux of the integrated water vapor, just reached Antarctica, just in the brought by this really intense low pressure system and intensified by the mesoscale cyclone. So this is the evolution of the event. If we look now into the cross sections during the peak of the event, so here we are on the 15th of February at 3 UTC, and we are looking at the cross section along the core of this corridor of the high integrated water vapor transport amounts, and on the right we have the perpendicular cross sections, so one in the lower latitudes and one just near Antarctica. So if we first focus on the cross section from Princess Elizabeth, so from Dronning Mountain to South Africa along the core of this atmospheric river, so we see a really interesting picture. So we have this really strong isentropic ascent. So we are in the warm conveyor belt and we have then the cold dome. So the isentropes are climbing really rapidly when they reach Antarctica. But here, this is the isentropic ascent associated with the warm conveyor belt within the exotropical cyclone. We have the really well-developed low-level jet, so more than 30 meters per second, around 900 hectopascal over the ocean, so around 55 latitude. And we see that it's related to the higher, the also intensification, so the upper level jet. And here we have the upper level jet actually. So there is a link between the upper level jet and the low level jet at the surface. And so the wind vectors, these are in yellow. And then we have the blue contours that show the specific humidity. So we have the strong, really the strongest values. They are near South Africa. So at the highest are near the surface. And here we see that there is the moisture is ascending along the isentropes. So we have the increase in specific humidity. So it's the maximum values follow the isentrope of 292 Kelvin. And we have in color, so this is the moisture flux. So we have the moisture flux greater than 250 gram per kilogram per meter per second within this axis. So we have this, the flux that is happening along this 292 isentrope, right? So, and this is the flux that is decreasing when it arrives into Antarctica, but still this is anomalously high for this region. And we see that it decreases drastically when it actually reaches the continent, but still these are again, I'm repeating myself, but this is the anomalous, anomalous values for this Antarctic region. So if you look then at the cross-section perpendicular over the lower latitudes, we have, the low-level jet coinciding with the humidity maximum. So this is the core of the maximum IVT. But then if we go to the cross-section near the Antarctic coast, we see that there is a decoupling. So we have the low-level jet staying near the surface, but the humidity maximum is actually at higher altitude. So this is what we see here. So the typical structure of the atmospheric river, as we see in mid-latitude studies and European, Californian studies, is actually very different in the polar regions. And this decoupling is very important. So we have the strong core of the river in the lower and mid-latitudes, and then we have the moisture transport at higher altitudes and the highest wind speeds near the surface. So and if we look at the fluxes along this atmospheric river event, so on the left, we have the latent heat flux in colors, and the dash contours show the sensible heat flux. So what is important here is that we have really strong evaporation in the lower latitudes. So here we see in red, so this is the heating of the atmosphere, right? So it's towards the atmosphere. But along the atmospheric river, so here we have in between the two fronts, so this is our atmospheric river, we actually have a strong suppression. So there is no evaporation. So there is really no moisture uptake along the atmospheric river. And I will show you later. So all this moisture that was reaching Antarctica causing anomalous precipitation was coming from lower latitudes. And also we have a strong heating, so the sensible heating of the atmosphere, of the surface, sorry, by the warm atmosphere. And we have, so this is during this the peak of the atmospheric river event. So when we have the really small moisture flux convergence during the event associated with the atmospheric river. However, during the development, so later during the development of this mesoscale cycle, we see that the picture changes. So we still have the suppression of evaporation, but we have much stronger moisture flux convergence. And here we have actually the contribution at the last moment. So maybe the second peak of precipitation actually was caused by this moisture flux convergence associated with the mesoscale cyclone. So and if we now change from the Eulerian point of view to the Lagrangian framework, so to actually explore, so what was actually all this moisture causing anomalous precipitation coming from lower latitudes? And the answer is yes. So we actually found that, so this is the region of the moisture sources which are responsible for precipitation. And here, so this is also the local moisture source associated with the mesocyclone event. So we do have a local contribution, but the largest contribution comes from this subtropical latitudes, which also showed the anomalous sea surface temperatures and anomalous evaporation that probably has triggered this event. And so here we actually isolated the trajectories with a condition that they should have more than 250 gram per kilogram per meter per second somewhere along the trajectory. So it was a bit of an arbitrary in a subjective way, but which is in concordance with the definition of the atmospheric river to associate the trajectories which are really explained by the atmospheric river transport. And if you look at the evolution, the thermodynamic variables evolution along these trajectories, we see the importance of the isentropic ascent, like during the event. So this is the theta, and this is the equivalent potential temperature. So we have the strong ascent, and this is the cold dome also, and the important contribution of precipitation and the moisture. We have the decrease of the sea surface temperatures, so which was also causing the suppression of the latent heat and the sensible heat. So we see this the strong evaporation and then suppression of the latent heat near to Antarctica. And we have the strong increase in specific humidity. So this is in yellow here. Just near the Antarctic coast, and we have the increase in the wind speed and the increase in the moisture transport. So this is in this way we could actually see the evolution. So what is actually happening along this trajectories, and we could explain that yes, the anomalous precipitation was actually linked to this extreme transport. So the transport of moisture from low latitudes, which was intensifying also in the mid latitudes and then reaching Antarctica. So this study is here we are using the ERA5 analysis, and the question is ERA5 is actually capturing well what is happening near in the Antarctic troposphere, and particularly during this atmospheric river events. So here we looked at the specific atmospheric river events which caused really strong increase in the moisture transport in the coastal joining mountains. So we looked at the Nomar station and also at the Sayovo station using the year of polar prediction measurements that I will be talking about later. So here the purpose was to understand the vertical structure of the atmospheric river when it hits the Antarctic coast, and also evaluates the reanalysis, so the ERA interim, the ERA5 reanalysis. So what we find actually when such an atmospheric river event hits the Droni Maudland coast, and this is a different event. So this is during the 2018 in December. So while this event was in 2018 in February, but this again, so it's also the summer event, and it's the same region. So we see that the radio zones, they show really strong increase in the coastal moisture transport, and the peak is actually found around 900 to 800 hectopascal. And we see that if you look at the temperature, so that it's really important that just during this event, so we have the temperature near zero, just at the height, at the surface, and at the height of the maximum precipitation, which is well captured by ERA 5, but it was not well captured by ERA interim analysis. So we see that the entire lower troposphere, so up to 500 hectopascal, is actually at the saturation. So this is with respect to ice. So its entire lower troposphere is saturated with respect to ice, and actually supersaturated at some levels. And we see the explanation for this moisture flux also, so that we have the increase in the specific humidity at the level of the maximum moisture transport. And we see this decoupling. So we have the low level jet, which is at the lower location. So here, and it's actually measured low level jet is not captured well by both ERA 5 and ERA interim. And while the humidity, you see that this peak, it was not captured by the ERA interim here, but this peak that was measured by the radio zones, ERA 5 captures really well. So we're really pleased by the performance of the ERA 5 reanalysis, and I would recommend to use it for Antarctica studies. So this is, we are talking about the coastal. So this where more problems exist in the interior of Antarctica. So if we look at the evolution, the temporal evolution of the atmospheric rivers on this, so during the year of polar prediction, so these are the profiles. So we have the month of December 2018, and here this profile is actually based only on observations of radiozones. 4 radiozones per day. So that was really intense observing period during the year of polar prediction from 2018 to 2019 during the summer period. And it was really a unique opportunity to use these observations and understand the structure of the atmospheric rivers. So what we see here, so then the upper plot, we have specific humidity, the wind speed, and the moisture transport. That so we have so during the month of December, so we have a strong, so we had 2 atmospheric river events with a strong increase in specific humidity, the wind speed, and the moisture transport. And as you see this, so the red lines that show the atmospheric river events that I identified using the algorithm. And you also see the white bars, which show the missing values. So these are, so we had the 4 radiozones a day. So they were launched by colleagues in Neumayer station. So here I'm showing just at the Neumayer station, and also at, so in this publication, I used the both Neumayer and Sayova station. And this is also an important message that, so with this intense observations, we could capture the atmospheric rivers still, but they were missed. So there were failures of the radiozones just during the atmospheric river events. And there were also a no-go periods because it's really dangerous, and some measurements were failures, and some they did not happen because personnel could not go and do the radiozone launches because of the safety issues. So this is really important to remember about these events, that we really missed them in observations, and we could capture them during this thanks to Neumayer and Sayova and other stations that were doing these measurements. And we could actually analyze and really do the analysis similar to this one with the vertical structure using the radiozones and evaluation. So if we use, then if you look at the climatology of the events, So here I show a composite using the radiosonde measurements during the 10 years, so from 2009 to 2019, composites for the atmospheric rivers compared to the median values. So the median is this gray values, and we have the observations in bluish, red is era 5, and greenish is era interim. So you see for temperature, first, so this is the annual, so it's all seasons. So we see this really important increase compared to median. So the surface temperature reaching 0, and also it's close to 0 at the higher altitudes, which is a huge jump compared to the median values of the surface temperature. And this is the at Sayova station. So then we have the increase in the huge increase in the specific humidity. So here the radiosondes and underestimated by the reanalysis, and a huge difference with the median values. Then we have the wind speed, low-level jet at around 900 hectopascal, and again, huge. So this is extreme state compared to the median values, and not well represented also by both reanalysis, while Euro 5 is closer. So we have the change in the wind direction, showing mostly the synoptic wind direction during these events. So here's the northeast at the station. And so the moisture transport, the total, and the zonal and meridional moisture transport. So we see the really small values for the median, and the extreme values explained by these atmospheric river events. And actually, I'm really running out of time, and I think I will try to go quicker through more material, and will answer questions. If I can take like 10, 15 more minutes, is it okay?
Sure, that's okay.
Okay, yeah, thank you, sorry. So I was talking about specific events and the case studies, and now I would like to show you the climatology. So this is the paper, so led by Jonathan William, just accepted, and JGR. So we are showing the climatology of the atmospheric river events, so the frequency of the events using the algorithm developed so by Jonathan. So we have two different algorithms, and actually compare really well. So my algorithm and Jonathan's algorithm. And here, so the applying this algorithm during the whole instrumental period from 79. So we see the frequency of occurrence of the atmospheric rivers in percentage during the days of the year. So here the percentage that is translated into the days, and you see these are really rare events. So the maximum we are talking about just 5 days per year, and mostly we are talking about 1 to 2 days per year. So when we see the largest frequency of occurrence over the Southern Ocean, and here they covering like the peninsula, and if we're talking about the coastal, so the joining mountain and the Adélie and Wilkes Land is really important. So if we are putting together the images, so as I showed earlier, from Turner et al, the extreme precipitation events and how much of this extreme precipitation events, the snowfall, are explained by atmospheric rivers, you can see that depending on the percentile of the events, so the most extreme, so the snowfall which are in the 99th percentile, actually the majority of them, so up to 90% in most regions, are explained by atmospheric rivers. If you go to the less extreme events, so 95th and the 90th percentile, so there is a fewer percentage of these events are explained by atmospheric river. So the atmospheric rivers are really responsible for the most extreme precipitation snowfall in Antarctica. But they're causing not only precipitation, and it's important to remember that we also have the rainfall that is occurring around Antarctica. And here, so this is actually the outcome from the MAR model, and also we have so another study which I have not included here, showing the rainfall from the observations around Antarctica. So we have a really important rainfall occurrence here in the Western Antarctic Peninsula, and also along the coast in East Antarctica and as well in West Antarctica. So in here, the contributions, so we see that atmospheric rivers, they contribute a lot to the snowfall, especially along the coast. but also they have a significant contribution to the rainfall, which has to be taken into account. So I will skip this as the seasonal distribution. So there are some differences. And so I would like to now talk about another extreme impact of the atmospheric rivers, which is increase in the temperature and increase in melt. So I will go back to the previous slide, but here this is the attribution of the major melt events over the West Antarctic Peninsula and over the West Antarctic ice sheet and over the Antarctic Peninsula to atmospheric rivers in summer and in winter. And we see that, so the majority of the winter events and also a large amount, so in this, especially in this area of the summer events, can be explained by atmospheric rivers. So it's not only precipitation, but also atmospheric rivers can cause the major melt over these regions. And it's important also that if we are looking at these specific regions at the trends of the Antarctic or of the atmospheric rivers, so we see that there is an increasing trend in the frequency of occurrence. And again, so this increasing trend, we are talking about less than 1% to up to 1%, and the peak during some years to 2%. So it's really a rare occurrence of atmospheric rivers, but the trend showing that there would be an increase in the occurrence of these rare events, particularly in these two areas. So it's a question, will they cause more of these major melt events as we see, or will they cause more of the extreme snowfall, or maybe they will be responsible for more rainfall in the future? So these are really the questions that we are also trying to answer, and hopefully that there will be more work by other groups. So if you look at this specific event that was causing really a major melt over the Western Antarctic ice sheet, which occurred in May 2016. So we see that there was really an important blocking. So there is the high pressure system, excuse me, that is blocking the low that is actually squeezing the atmospheric moisture transport just in between these two systems. And if you're looking back at the climatology, so the composites, we see that the atmospheric rivers, if you do a composite of these events, so they're actually associated typically with this type of blocking. So this is the anomalous at 500 hectopascal. So we see that this is a really typical the blocking situation that caused the atmospheric rivers, which also are responsible for the warm events. So here, this is the events or the West Antarctic ice sheet, so the blocking over the Amundsen-Bellinsgausen and the low pressure located just down the stream here. So the atmospheric rivers, they are associated not only with the high moisture transport, as we can see here. So for this event in May, so we have this, so the contours is actually the two algorithms, the Jonathan's and mine, and they show really good agreement. And we have this really large increase in the integrated water vapor transport and the amount. But what we see also is a really large increase in the ice and supercooled liquid in the clouds. And here I'm showing the net radiative forcing from the clouds within the atmospheric river, which was a really huge effect during this major melt. But at the same time, we have an increase in the sensible heat flux. So we have the heating of the surface and also over not only over the ocean, but also over the ice sheet, and especially in this area of the peninsula where we have the Föhn events. Because if you look at a different event in the March 2015, which was associated with the record high temperature and the ice disintegration. So we have really important coupling between the extreme moisture transport, the precipitation formation. So these are also the cloud radiative forcing, and there was this the Föhn effect in the lee side of the Antarctic Peninsula. So and just to talk more about this event, well, I will quickly show you so this is the work of Bozkurt and Tola in 2018, showing this March event. So that was causing the increase in the temperature over the Antarctic Peninsula and a record high temperature at Esperanza Station. And the disintegration of the fast ice and mole ponds really during the event. So we see this really happened, very fast disintegration. And so the temperature extremes, and this work shows the connection between the atmospheric river and the Föhn event. So I don't have time to go in details, but just wanted to stress, to bring your attention to the important, again, another extreme role of in temperature record and in melt. So, and I would like to now quickly go over the ongoing effort. So the measurements that have been done using the international initiative of the Year of Polar Prediction. So this is one of the key goals is also to capture this extreme events. And it's an international initiative with the stations around Antarctica and especially in the peninsula. So in here we were actually collaborating with the colleagues at Escudero and the Sayova at Neumayer station, and also in the Punta Arenas to study atmospheric rivers. And just to show you how intense can be the measurements during this event. So these are the measurements at Sayova station. And just show this again. And this is the profiles that we have been using to understand the atmospheric rivers. So it's really huge thanks again to the colleagues who have been doing these measurements. So and thanks to these observations, we could again understand the vertical structure using the observations so in the lower troposphere. So and this is the similar to previous plots. So we have the radiosonde observations in solid lines, and then I'm comparing to the ERA 5 and ERA interim. And we see again, so the observations showed really an importance of this near surface, about 900 hectopascal moisture peak, which is explained mostly by the low-level jet and the increase in the specific humidity, and also the really strong increase in the temperature during this event. And we see that the models, so the ERA 5 and the interim analysis both struggle with reproducing this peak in the moisture transport. So we have to still understand what is happening in the models and what we need to improve the processes. So I will skip. So these are the similar conclusions we had for Sayova and for Neumayer station. And for Neumayer, actually, it was a better comparison of ERA 5 compared to observations, particularly for specific humidity, but not for the low-level jet. So another effort that we have been doing is using again this Year of Polar Prediction measurements, and we have to understand the events at the Antarctic Peninsula. So in here we are really lucky because there was several Year of Polar Prediction projects that were in place. So we have actually the projects at the Escudero station, so on King Sejong and King Sejong stations, so the Chilean and the Korean stations, both located on King George Island. And also we had the observations from Punta Arenas, so from the colleagues from Tropos. So in these observations allowed us to measure simultaneously at these two locations the really extraordinary atmospheric river events. So we see that the event which is extending from the subtropical South Pacific, going into the southern Chile, into the Atlantic Ocean, and then reaching the Antarctic Peninsula. So that was really an important event to study, which we are still analyzing. So we actually contributed to the overview paper by Bromwich et al. Published in BAMS. We have a specific section on the atmospheric rivers where we show these results, and now we have another publication in preparation where we are looking at these events from different perspectives. So what are the vertical structure, what are the cloud properties, what are the radiative surface, fluxes at the surface, what is the precipitation, and so on. So we were again lucky to have observations from the Punta Arenas and from the King George Island. So here we can see, for example, the evolution of the liquid water path measured at Punta Arenas, the integrated water vapor, a huge peak during the atmospheric river, again at Punta Arenas. So then we have the dots is the radiosonde observations at the King George Island. So we can actually analyze the evolution of this event in detail, and also compared to the radiosones that were launched, so extra radiosones launched at the Escudero station, that were showing again the importance of this upper level peak in the moisture transport here, the increase in the temperature greater than 0 degrees Celsius, and the huge increase in specific humidity. And we see that again, the ERA 5 and ERA interim were struggling with representing these peaks in specific humidity and temperature and moisture transport. So these events were associated with the transition from snowfall to rainfall. And this is what we are studying, we're analyzing now, because these events show that this the increase in the temperature to greater than 0 degrees, and then we have these fluctuations to sub-freezing and above freezing temperature during several events measured during this summer year of polar prediction period. And this is really important because we could capture this transition from snowfall to rainfall and from rainfall to snowfall during one event. And as well, we were using this observation. So this is the work of the colleagues from Korea, who were using this extra radiosonde observations to do a simulation in the WRF model and to study the effect on precipitation. So and here we see that. This is the model output showing there was a small improvement. So this is not an extreme precipitation event, but it was a good example. So we see it was really medium precipitation amounts at the King George Island, but it was a really strong orographic enhancement in the western side of the Antarctic Peninsula. So this is ongoing work, and so the summer year of polar prediction is over. So it was in 2018-19, and now we are preparing a new campaign, so which will happen in April, July 2022. So this is the focus on winter. And what we would like to do is to have targeted observing periods, and the atmospheric rivers will be one of the interesting events that we would like to target. And so we have 3 regions now with the 3 core groups planning these observations. And we have really a lot of great colleagues from different stations and a lot of young scientists involved in this preparation. So, and I will be happy also to talk more about this, who is interested also in joining this effort. So, and I would like to also quickly touch base about the connections. So I will not talk in details about the Southern Ocean measurements, but we had also the precipitation and atmospheric river measurements during this Antarctic circumnavigation expedition, so which happened in 2016-17, so on board of the Russian icebreaker. So we were launching radiosones also during the atmospheric rivers, and we had a bunch of precipitation measurements. So we were measuring precipitation with the microrain radar and also with the snow particle counter, and so here in Zoom, and also with the Wengler particle counters. So we are actually doing now the analysis comparing these different precipitation measurements. And we're also using this really old and very nice technique, using formula regime, when we're capturing we're casting, so not capturing, but it's the casting of the snowflakes. And then we have a collection of these different, so the slides with this imprints of the snowflakes, which we're then analyzing with the high resolution 3-dimensional scanning. So, and we are actually have information about the microphysics, so the shape and the size of the snowflakes. So I don't have time to go in detail. I just wanted to show you that, so the work in progress, so we're actually looking at the evolution of precipitation using different inputs. So from the microrain radar and from the snow particle counter, and looking at the differences and the changes in the microphysical properties, which are changing actually along during the same event. There were a lot of changes in the microphysical properties of, so the shape and sizes of the snowflakes. And we're also collaborating with a really great scientist, artist who is working on the on the transition between the science and art. So Yvonne Weber. So this is her work. So we are also collecting the so similar former images of the snowflakes, but on a larger frames. And she's actually using these images and the three-dimensional scans and just the photography to have really beautiful images. And this is just an example. To talk about the properties of snow, the Antarctic precipitation, and climate change. So I will try to summarize if possible, because there are a lot of actually a lot of ongoing work and a lot of questions to answer, but to try to give you some takeaway messages is the importance of the large interannual variability in Antarctic surface mass balance that is actually overlying the occurring mass loss from the Antarctic ice sheet, the important role of extreme snowfall events, and especially those associated with atmospheric rivers. Also a reminder that atmospheric rivers can cause not only extreme snowfall, but also extreme melt events and can cause rainfall. And they have also strong increase in the cloud, radiative forcing, and so on. So there is really complex processes that are happening during the atmospheric rivers. And what we are doing is to, we are trying to have more measurements of both vertical structure of the atmospheric rivers and also measurements of precipitation in Antarctica, so over the ice sheet and the Southern Ocean, to improve our understanding and evaluate, and also be able to evaluate and improve models, so both regional climate models and the global models. So thank you very much for your attention, and I would like to thank a lot of colleagues who have contributed to this work, and the list is really long. I was trying to put it on the last slide, but it was not possible because it is an international effort doing the measurements and modeling and understanding the atmospheric precipitation and the surface mass balance, especially using the observations. And thank you very much for your attention, and I will be happy to discuss with you and have your questions, and please also send me an email later. So thank you very much.
Thank you. That was great. Everybody's putting little clap emojis for you. So we have a few minutes for questions. So we first want to open it up to students or early career researchers. So if any of you students or early career scientists have a question, please go ahead and raise your hand or put something in the chat. I'm going to wait a minute to see if anybody does. Yes, Ian.
Yeah, hi, thank you very much for the talk. Very interesting. I was wondering about the vertical structures of the atmospheric rivers, and the definition that I'm typically familiar with is that there's a structured cold front involved with the river. And I'm wondering if, since you've seemingly looked at a lot of these, whether you find like physical differences, like meaningful physical differences between ARs that might be associated with strong cold fronts, or those that are just diffuse regions between a high and a low pressure.
Yeah, that's a very good question. So the atmospheric river, so the case studies that we looked at, they were always associated with the cold front. So the image that I showed, and I will not go all the 50 slides back, I think, but well, I can try to show it again. But the pre-cold frontal position of the atmospheric rivers. So this is also typical for the Antarctic atmospheric rivers. The difference with mid-latitude atmospheric rivers is mostly in this decoupling. So when we have we have this pre-cold front low-level jet, and the typical. So if you saw the schematic of the atmospheric rivers in mid-latitude, so we have the low-level jet, pre-cold frontal, right, and the moisture flux and the low-level jet at the same position. So when the atmospheric river reaches Antarctica, so actually we have the really strong rise, so along the warm conveyor belt, and also associated with the orographic enhancement in a lot of situations, if it's in the peninsula or in the Johnny Mountain, for example. And then we have the decoupling of the moisture compared from the low-level jet. So this is the difference with the mid-latitude schematic and the image, not just schematic. Did I answer your question?
Yeah, thank you very much.
Yeah, thank you.
We have time for one or two more questions. Oh, we have one in the chat. So Noah Chen says, have there been efforts to assimilate observations in Antarctica into reanalysis data?
Yes, and actually so all the year of polar prediction observations, they are in the GTS. So they are in the automatically assimilated in the reanalysis. So then there were the radiation denial studies, and like the one also I showed, like for the polar warp studies by Korean colleagues using the Antarctic Peninsula measurements. And there are also some observations. So the observations we did during the ACE, so the Southern Ocean expedition that I showed last, so they were not assimilated. So we are actually, so we have to make them part still of the global system. But all the stations, so the stations around Antarctica, so when they have this intense observing period, so all these observations are used right away as a simulation. So,
other questions? We have time for about one more. Anyone? All right, if not, let's thank Dr. Gorodetskaya again for the great talk. And thanks everybody for coming this morning, this afternoon in Portugal.
thank you.